Hi everybody, welcome to my talk about Ray and Anyscale. We're going to be covering an optimization journey in how we were able to start with a simple use case using Ray and power it using Anyscale. Before we begin that, I want to give a quick outline of what I'm going to be speaking about today. So just going to cover the people involved in this talk and the presentation, the problem statement that we were trying to accomplish, what we tried out first, fourthly, how we improved that, and then a fifth step in what our final state looked like, where we were able to achieve really good scaling. So to begin, my name's Nachi Mehta. I'm a co-founder at oxdub.io. We're a consulting company that primarily focuses on data engineering, analytics, and data science. I was helped a lot in this journey by Charles Greer. He's a solutions architect at Anyscale. He's been with me pretty much every step of the way in this process. In addition, I just want to give a couple shout outs to some of the other people at the team here at Anyscale. Bill Chambers had a product. Archit Kulkarni, he helped us as well. And Simon Moe was really critical at certain phases in addition. So to begin, the problem that we were trying to solve was to deliver a scalable machine learning application that predicts product affinity based on a user engagement history. And it had one non-functional requirement, was that it had to be modular in design so that it wouldn't conflict with the existing code base for our client. And we wanted to allow for future changes of the model and the way business logic handled the output of the product, the prediction of the model. So to give a very high level, and when I say high level, I mean very high level overview of the architecture. Imagine a user, you get user data coming in from a mobile SDK, and that is processed by some business logic, an application or a server that the client possessed, and they will send that data to Elasticsearch, where the data was ultimately stored. After that, we used our Anyscale cluster to grab that data, and we were able to build a model, train it, and then score based on the data that was housed there, and send that score back to the original service so that it could decide what to do for the user, and eventually send that back through some sort of user interface in a mobile application. So our first attempt at solving this problem for our client was to create a model in Anyscale and Ray such that it could set up an endpoint for us that the client could hit without as a normal REST endpoint and get back a prediction. And the way this works is fairly simple in Ray. What we're able to do is use Ray serve that creates an endpoint for us by plugging in the Python model you like and any associated parameters. The model class itself looks like this, where it has a predict method that's eventually called by this magic method call, which is something that all Ray serve endpoints are looking for. What it does here, I'll walk you through the code very briefly, is it gathers the data from Elasticsearch, and it sends that data into our compute click frequencies, and it gets the user preferences. If everything checks out, it returns the response. So all we need to do to start this is run the endpoint class, at which point we'll be able to see our backend running. And you can see that here. Hotel recommender model is now running. So if we want to test this, we're going to run a small load using this local software that I have installed named Locust is a load generation tool. And I can start swarming this here. Now, what we're going to see is that the load is actually much higher than what we're able to get back at requests per second. And the reason for this is because the way we've set up our class initially is every single request coming from this endpoint is contacting, reaching out to Elasticsearch, grabbing the data, doing a calculation, and sending it back. This is inefficient. So we need to figure out a way to cache that result. So our ultimate problem is, how do we separate the caching of the search results from Elasticsearch with what the model needs in order to predict? So the way we do that is using the Ray object store, which creates a shared in-memory retrieval mechanism so that we can distribute that across our cluster and be able to use the data whenever we like without having to reach out to Elasticsearch every single request. In order to make use of the Ray object store, we simply need to implement two methods. One is Ray put, which puts the data into the Ray object store. So in order to do that, we have to extract out all of the Elasticsearch code that was originally in the hotel recommender model and put it into our serve script. That way we can inject the reference to the output of that data into our hotel recommender model. And what this allows us to do is every time the endpoint is called, instead of reaching out directly to Elasticsearch, we're now reaching out to the object store, which makes things much more efficient. If we take a look at the second method, we need to implement ray.get. And here we've just instantiated the model with its own private member variable so that it knows how to get access to that Elasticsearch data reference. So now if we take a look at a new test we can run on this new backend, we'll be able to see that our requests per second are going to be much higher than the 1.5 that we had before. So if we let it run for a minute, we'll see it should go up to around 5 or 6 requests per second on a single instance, which admittedly is not as high as we'd like, but it's a much larger improvement from only 1 or 2 requests per second. So our next logical question was, how do we scale this up from a very small few requests per second to a much higher requests per second that is realistic for production? So we had to implement something called the Ray actor model. And what the Ray actor model enables us to do is abstract away and encapsulate the call that is made to Elasticsearch so that results can be updated, cached, or retrieved within the distributed computing engine. Before, just storing the results in the Ray object store, there was no way to scale that across nodes and clusters because the reference to that object would eventually be garbage collected. But once it's kept inside of a actor, that won't happen. And in addition, we would be able to add hooks to update the reference whenever we like. So how does this happen? Well, we create our infinite scaling hook by creating a second backend. Once the actor model has been implemented inside of our serve script, which serves back the recommendation API that we've been working with in the beginning. Now to implement the actor model, we're going to go back to our serve script and create another class, which we've called data holder here, and annotate it with the Ray remote annotation. And all we're doing is we're taking the Elasticsearch piece of code and putting it inside of the data holder class. That way it will be able to preserve the response data that's coming from Elasticsearch, we use the Ray Object Store here to put it into the Ray Object Store. That way, when another class needs to access it, specifically the hotel recommender model, it will be kept alive across different contexts within the cluster. So we're going to demo for you here how we are able to scale this up and down using another script with another backend that's just as easy to deploy in a few lines, that sets up a hook for us to scale up and scale down. All you need to do is hit this endpoint, and it's giving us increasing the number of replicas on our backend, which was described here as HRV1. If you go back, that has to match here, the create backend HRV1 tag. So what we can do is launch our locust cluster again to start generating load, and we'll see a little bit of a few requests here coming in. Now what we can do is we'll jump back and we're going to scale up our cluster. And let's scale it up just a tiny bit more. And if we jump back here, we should see these requests go up in time with the amount of scaling that we did. So you see we started the beginning of the demo at only 1. We've achieved 17 times effectiveness, and you could potentially see this going more and more. As you can see on the dashboard, we have 4 replicas going. If we scale it again, this will increase the number of workers and we'll get even more ability to scale out. And with that, we've ended the presentation. I'd like to thank you all for watching my talk. Again, my name is Nachi, and I'm a co-founder at oxdub.io. Feel free to reach out. My email is nachi@oxdub.io. In addition, if you'd like to learn more about Anyscale, you can find them on the website there at anyscale.com, or contact us on the Ray Slack, and you can also message Charles directly at cgreer@anyscale.com. Thanks again.